This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today we're diving into a fascinating paper that explores the intersection of artificial intelligence and artificial life. The title itself is intriguing: Automating the Search for Artificial Life with Foundation Models. It promises a significant leap forward in a field that's been largely reliant on manual design and trial and error.
Precisely. For decades, researchers in artificial life have painstakingly crafted simulations, hoping to observe emergent life-like behaviors. This paper proposes a radical shift, using powerful AI models to automate that very search process.
That's a game changer. Instead of relying on intuition, researchers could now systematically explore vast spaces of possible simulations. What are the implications of this?
The potential is enormous. Imagine accelerating the discovery of new life forms, understanding the conditions that give rise to complexity, and even quantifying previously qualitative aspects of artificial life.
It sounds almost too good to be true. Let's delve into the specifics of how this automation is achieved. The paper introduces a framework called ASL, or Automated Search for Artificial Life. Can you explain the core concept behind ASL?
ASL leverages foundation models, specifically vision language models like CLIP, to evaluate the output of artificial life simulations. These models are trained on massive data sets and have a remarkable ability to understand and interpret both images and text.
So the AI essentially watches the simulation and judges its interestingness?
Exactly. But the interestingness is multifaceted. ASL uses three distinct search methods: finding simulations that match specific target behaviors, discovering simulations that exhibit open-ended novelty, and illuminating the entire space of diverse simulations.
Let's break down those three methods. First, the target-driven approach. How does that work?
In the target-driven approach, the researcher provides a textual description of the desired behavior. ASL then searches for a simulation whose output video matches that description, as judged by the foundation model. It's like giving the AI a prompt, such as a self-replicating structure, and letting it find the simulation that produces it.
And you've seen this work in practice. What kind of results have been achieved using this target-driven approach?
Yes, the paper demonstrates successful results across various substrates, including linear, Boids, and particle life. For example, by providing a prompt like a swirling pattern, ASL successfully identified simulations within these substrates that produce precisely that pattern. These were often novel patterns not previously observed.
That's impressive. What about the second method, the search for open-endedness? This is a key concept in artificial life, isn't it?
Absolutely. Open-endedness refers to a system's ability to continuously generate novel and interesting behaviors over time. It's a hallmark of natural evolution and a major goal in artificial life research. ASL tackles this by searching for simulations whose trajectories through the foundation model's representation space show high historical novelty. Essentially, it looks for simulations that consistently surprise the AI.
How does ASL quantify this surprise or novelty? Open-endedness is notoriously difficult to define, let alone measure.
That's true. The cleverness here is that ASL leverages the foundation model's representation space as a proxy for human perception. Novelty in the AI's representation space is assumed to correlate with novelty as perceived by a human observer. The paper shows that this approach successfully identifies open-ended simulations, including some cellular automata that rival the complexity of Conway's game of life.
And the third method, illuminating the entire substrate? What does that entail?
This method aims to discover a diverse set of simulations, effectively mapping the space of possible behaviors within a given substrate. ASL achieves this by searching for simulations that are maximally distant from their nearest neighbors in the foundation model's representation space. This creates a kind of atlas of diverse artificial life forms.
The paper emphasizes that ASL is substrate agnostic. What does that mean, and what substrates were used in the experiments?
Substrate agnostic means that the method can be applied to a wide range of artificial life simulations, provided they can be rendered as images or videos. The paper demonstrates this by applying ASL to several substrates: Boids, particle life, various cellular automata, linear, and neural cellular automata.
And what about the choice of foundation model? Is ASL tied to a specific model?
No, the paper explores the use of both CLIP and DINOV2, demonstrating that ASOL is relatively agnostic to the specific foundation model used. While CLIP, a vision language model, performed slightly better in some aspects, both models significantly outperformed simpler, pixel-based representations. This highlights the importance of using high-level, semantically rich representations for evaluating the interestingness of artificial life simulations.
Beyond discovery, the paper also suggests that foundation models can help quantify aspects of artificial life that have traditionally been considered qualitative. Can you elaborate on that?
Yes, the ability of foundation models to embed simulations into a meaningful representation space allows for quantitative analysis of emergent behaviors. For example, the paper demonstrates how to quantify the importance of different parameters in a simulation or how to measure the plateau of a simulation's development, indicating when it has reached a stable state. This opens up new avenues for analyzing and understanding the dynamics of complex systems.
The implications of this research extend far beyond the immediate applications demonstrated in the paper. What are some of the broader implications and future directions?
The potential is truly vast. This approach could be extended to other domains, such as low-level physics research, where the goal might be to discover fundamental laws or equations that govern the universe. Furthermore, the use of more advanced video language models or 3D models could allow for the analysis of more complex and realistic simulations. The integration of large language models could even enable the automated design of the substrates themselves, leading to a fully automated scientific discovery process.
It's remarkable to think about the possibility of using AI to not only discover new life forms, but also to design the very environments in which they evolve. This seems to be a significant step towards understanding the fundamental principles of life itself.
Precisely. The work presented in this paper represents a significant advancement in our ability to explore the vast landscape of possible life forms, both artificial and perhaps by extension natural.
Of course, there are limitations and challenges. What are some of the potential pitfalls or areas that require further research?
One key challenge is the selection of the appropriate substrate. While ASL is substrate agnostic, the choice of substrate significantly impacts the types of emergent behaviors that can be observed. Finding the right balance between simplicity and expressiveness is crucial. Another challenge is the potential for bias in the foundation models themselves. These models are trained on data that reflects the biases of the real world, and these biases could influence the types of simulations that are deemed interesting. Careful consideration and mitigation of these biases are essential.
So the success of ASL depends not only on the power of the foundation models, but also on the careful design of the simulation environments and the awareness of potential biases. Let's summarize the key findings of this research. What are the most significant contributions of this paper?
The paper's primary contribution is the introduction of ASAL, a novel framework for automating the search for interesting artificial life simulations. This framework leverages the power of foundation models to overcome the limitations of traditional manual approaches. ASAL demonstrates the feasibility of using AI to discover target behaviors, open-ended novelty, and diverse simulations across a range of substrates. Furthermore, the paper highlights the potential of foundation models to quantify previously qualitative aspects of artificial life, opening up new avenues for research and analysis.
This research truly opens up exciting new possibilities for the field of artificial life. It's a testament to the power of combining AI with other scientific disciplines. Looking beyond the scientific community, what are the broader societal implications of this research?
The long-term implications are difficult to fully predict, but the potential impact is significant. A deeper understanding of the principles of life, both natural and artificial, could have profound implications for various fields, including medicine, biotechnology, and even our understanding of the universe itself. The ability to automate scientific discovery could accelerate technological progress and lead to breakthroughs in various areas. However, ethical considerations surrounding the development and use of advanced AI systems must be carefully addressed.
Indeed. The responsible development and deployment of AI are paramount. Are there any specific concerns or ethical considerations that you think researchers should be particularly mindful of as this field progresses?
Yes, several ethical considerations need careful attention. The potential for misuse of this technology is a significant concern. The ability to automate the design of complex systems could be exploited for malicious purposes. Furthermore, the potential biases embedded within foundation models could lead to unintended consequences. Researchers must prioritize fairness, transparency, and accountability in their work. Robust evaluation methods are needed to ensure that the simulations generated are not only interesting but also ethically sound.
This highlights the importance of interdisciplinary collaboration between AI researchers, ethicists, and policymakers. Does this automation of the search for artificial life diminish the role of human intuition and creativity in scientific discovery?
Not at all. In fact, I believe it enhances it. By automating the tedious and often unproductive aspects of the search process, ASL frees up researchers to focus on higher level questions, formulating hypotheses, interpreting results, and guiding the direction of research. Human creativity remains essential in defining the research questions, selecting appropriate substrates, and interpreting the results generated by the AI. The collaboration between human ingenuity and AI power is synergistic.
So it's more of a partnership than a replacement. This discussion has been incredibly insightful. To wrap things up, what's the most important takeaway for our listeners?
The most important takeaway is that this research represents a paradigm shift in artificial life research. The automation of the search process, enabled by foundation models, opens up unprecedented opportunities for discovery and understanding. However, responsible development and deployment of this technology are crucial to ensure its ethical and beneficial use.
And what are the next steps in this research? What are some of the key areas that need further investigation?
Further research should focus on refining the search algorithms, exploring new substrates, and developing more robust methods for evaluating the interestingness of simulations. Addressing the potential biases in foundation models is also crucial. Ultimately, the goal is to create a fully automated system for scientific discovery in artificial life, but this requires careful consideration of ethical implications and ongoing collaboration between researchers and policymakers.
It's a fascinating field with immense potential, but also significant challenges. Thank you for shedding light on this groundbreaking research.
My pleasure.
That was a great discussion.